Hi, welcome to a revision lesson on non-replacement probability. Okay, this is an A-star maths topic. Okay, where you can draw tree diagrams if you want, but you don't have to. Okay, the biggest thing to remember on this is that the fractions will change throughout the question because what you do on the first event affects what happens on a second event. Okay, some people call it dependent probability. And my example I've got there, look, if I take a white chocolate from a box, two things are going to happen. There's going to be less white chocolates in the box, but also the total number of chocolates is going to decrease as well. Okay, so the probability of me picking the first white chocolate is going to change all of the other fractions for when I pick my next chocolate, which I definitely will be picking at least one chocolate. Okay, so you don't need to write this down necessarily, but if you want to, you can. Now what I've got there in red, this is the bit that I find trips up most people when they get to your 11 GCSE past papers and ultimately in the exam. Because they're not actually writing down the combinations they're using, they generally tend to miss a combination, okay, or repeat one by accident that they shouldn't have, okay. So what I would say the key in this topic to getting full marks and not doing something stupid is to write down your combinations. So things like, black and black, red and red, white and blue. Write them down first, then get into your fraction work afterwards once you've sorted out that you've got all the combinations correct. Okay, just a quick reminder before we get into a question. The word and in probability is multiplying and the word or is adding. Okay, you'll do and at the beginning of questions when you're doing your combinations, and you'll use the or rule at the end when there's more than one way of doing things. You need to add up all those different combinations. Okay, right, so let's have a look at our question. First question. Okay, what I'd like you to do for these, I haven't got many, just for these couple of questions, is to write the question down. Okay, if you think you can write it in less words, then by all means do. Okay, so for instance, what you can write, instead of probability of picking two reds, you can do capital P brackets two reds, and that means the same thing as just writing a sentence. Okay, and here look, you could write P brackets different colors. Okay, so what we've got in this box is 6 reds and 4 blues. So on your first pick there are 10 discs, so both fractions are out of 10. 6 of them are red, 4 of them are blue. Okay, so if I went like this, if I went red, 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 this is the 6 red ones, and then we've got the 4 blue ones. So when we first start, that's the contents of the box: 6 reds, 4 blues, 6 out of 10, 4 out of 10. To fill up the next part of the tree then, so let's do the top half. So let's come up here, up this little pathway that says we've just picked a red. So if we've just picked a red, I can scribble out one of those, look. And now what are we left with? Well, there's still some reds, but there's not as many. There's now only 5. And there's still lots of discs, but only 9 where there was 10. Okay. And there's still some blues, 4, because that's not changed because we didn't take any blue ones out, but now it's 4 out of 9, whereas originally it was 4 out of 10. Okay. Now, when I want to fill out the bottom bit of this tree, so let's get rid of that. And let's say, well, what happens if the first one we pick is blue? So, and let's get rid of this as well, because we're going back to how we originally were. So if I took a blue one out, then when I go back to the box for my second pick, there's not 4 blue ones anymore, there's only 3. So 3 out of 9. And this is a bit where some people get thrown. It looks like one of the red ones has gone back in, because we go back to 6 over 9. It's not that I've put it back in, it's that I never took it in the first place. Remember, why are we in the bottom half of the tree? It's because on our first pick we took a blue one. So we've still got 6 reds in there. We've started the whole thing again and said, well, what if I took a blue in and not a red on my first pick? Okay, so just be careful. A little trick you can do just to make sure you haven't done something daft. If you look at your numerators, look, 5 add 4 makes 9, 9 out of 9 because branches have to add up to 1. And then 6 add 3 also makes 9, so 9 out of 9, it adds up to 1. Okay. now we can answer the two questions. What's the probability of picking two reds? So if I get rid of this highlighted line here to show you the sort of the path, the route, the combination. So red and red, so up there and then up there. The probability of getting red and red, oh dear, red and reds, that's another way of saying two reds, but with and I know it's now times in, is 6 out of 10 times 5 out of 9. Multiply the numerator as 30, multiply the denominator as 90, and don't simplify that, okay? Because if you needed to use the OR rule later on, they'd need to have the same denominators. So don't simplify your answers in probability, unless it specifically says to. Right, then it says the probability of getting two different colours. Now this is where you're going to need to have a look at ways of doing that. So combinations. So I could get red and blue. That's one way. So I'll highlight that. So one way of getting two different colours is my first one is red and my second one is blue. But then there's another way where my first one is blue and my second one is red. So I write down my combinations first. So we've got R and B, and then we've got B and R, and they count as separate because they're the different way round to each other. So for red and blue, we've got 6 out of 10 times 4 out of 9, so that's 24 out of 90. For blue and red, we've got 4 out of 10 times 6 out of 9. This isn't going to be a surprise, it's got the same probability, 24 out of 90 again. And then we can say, because we don't mind which, red and blue or blue and red, we can add those together at the bottom. And so this is why we didn't simplify. 24 out of 90 add 24 out of 90 is 48 out of 90, your final probability of getting two which are different colours. Okay. Another way of doing that question would have been to calculate the probability that they were the same colour, so red and red or blue and blue, and then taking that away from one. Okay. So sometimes you can make things a bit quicker if you do like the opposite question, if there's less combinations. You won't know until you write the combinations down though. Okay. Right, next one. Again, write this one down. If you think you can shorten it, then by all means do. So in a raffle there are 3 bottles of wine, 4 boxes of chocolate and 2 gift vouchers. And we're going to look at the probability that the first 2 winners both take the same prize first of all. So I've got a tree here. So let's get this filled in. So to begin with, there are 9 prizes. 3 add 4 add 2 is 9. So there's 9 prizes initially. So when the first winner gets up and goes to get their prize, there's a 3 out of 9 chance they'll take the wine. There's a 4 out of 9 chance they'll take the chocolate. And there's a 2 out of 9 chance they'll get the gift vouchers. Okay. So let's now have a look at this top little clump of workings here. And why are we up here? It's because the first winner has taken one of the bottles of wine. So the chance of the next person getting wine, well, there's only 2 bottles of wine left, and there's now only 8 prizes. There's still 4 boxes of chocolate left, but out of 8, and there's still 2 gift vouchers left, but again, out of 8. And 2 add 4 add 2 is 8. Get rid of that. What if the first winner had actually taken a box of chocolates? What prizes would be left for the next person? Well, there would still be 3 bottles of wine. There would only be 3 boxes of chocolate, and there would still be 2 gift vouchers. Okay, there's supposed to be an 8 there. And again, 3 add 2 makes 8, 8 out of 8. Okay, but then start again. So let's rub that out and say, well, what if the first prize winner took one of the gift vouchers? What prizes would be left? Well, there would be 3 bottles of wine left for the next winner. There would be 4 boxes of chocolates, but now there would only be 1 voucher. Okay, so that's where you've got to be really careful, is getting the right fractions depending on what already happened. When a bottle of wine was taken, there's less bottles of wine. If a box of chocolates gets taken, there's less boxes of chocolate. And if a voucher gets taken, there's less vouchers left. but whatever you do, the denominator is going to change as well because there's less prizes to be won. Okay, so let's do part A then. So winning the same prize, and the ways you can do that, you could have that they both take wine, so wine and wine. They could both take chocolate, so chocolate and chocolate, or they could both take a voucher, voucher and voucher. And it doesn't matter which of these combinations happen because they all answer the same question, which is that they both took the same prize. So we've got the or rule in between these, so we can add them up at the end. So wine and wine, or chocolate and chocolate, or voucher and voucher. Okay, now then, using my tree, wine and wine is 3 out of 9 times 2 out of 8. Just follow the path, so 6 out of 72. Chocolate and chocolate, so this is going straight across, so 4 out of 9 that the first person takes chocolate, 3 out of 8 that the next person does, so that's 12 out of 72. And the voucher is going to be the least likely because there's less vouchers in there, so we've got 2 out of 9 that the first prize winner takes a voucher, and there's a 1 out of 8 chance that the next person does as well, so that's 2 out of 72. And then we said we don't mind what prize it is as long as they're the same, so we add all of these up now. Okay, they've all got the same denominator because we didn't simplify, and what you end up with there then is 20 out of 72. That's the probability that the first two winners take the same prize. Okay, now if you look at part B, part B says, well, what's the probability that they all take different prizes? Well, there's loads of ways of doing that. If I write the combinations down, we could have wine and chocolate. We could have wine and voucher. We could have chocolate and wine. We could have chocolate and voucher. We could have voucher and wine, or voucher and chocolate. So I could do each of those 6 combinations individually again. They'd all be out of 72 again, add them all up, and I would get the probability of the first two winners taking different prizes. But actually, if you think about it, taking different prizes is the opposite of taking the same prize, and so we can actually use a shortcut for this. It's 1 minus the probability of them getting the same prize, as long as the two things are total opposites. Okay. So 1 in this case is 72 out of 72, because you've got to write it as a fraction. Take away 20 out of 72, which is what we worked out here, look. And that leaves us with 52 out of 72. That must be what those 6 combinations add up to, 52 out of 72, because between them they make 72 out of 72, okay, which is a whole. You don't have to do it the one takeaway method, but it's time saving if you can spot it. Okay. And then part C, what is the probability that the first 3 winners? Now I can't use the tree for this because I don't have the third set of branches. Okay, so we're going to try and do it without. So how many boxes of chocolates were there? There were 4 to begin with, 4 out of 9. So without the tree, look. The first person taking a box of chocolates is a 4 out of 9 chance. And, so times, the next person taking one, well, there's only 3 left out of 8. Okay, so there's a 3 out of 8 chance that the second person is going to take a box of chocolates. And when a third person comes up, there's going to be a 2 out of 7 chance now then, because there's another box of chocolates gone. Times all those together, 4 times 3 times 2 is 24. And 9 times 8 times 7, oh, God knows what that is. So 72 times 7, 490, 504, is it? Okay, you might want to check that on your calculators. I haven't got one handy. But it's 490 plus 14. Yeah, that's got to be right. Okay, so that's the chance that the first 3 winners all take a box of chocolates. Okay, without the tree, that's just reducing the number of chocolates that were left for the next person to pick. Okay, another example then. And I'm going to see if I can do this one without a tree this time. Okay. So, in a sock drawer there are 4 white socks, 5 grey socks and 8 black socks. Mr. Mackenzie gets dressed in the dark, as you may have noticed in school, and so he picks his socks at random, and because he's particularly lazy, they're all individual single socks. He doesn't even pair them up. Okay, calculate the probability that he picks a pair of grey socks. Now in probability talk, getting a pair of grey socks is like saying that he gets grey on his first pick and grey on his next pick. Okay, so what's the chance of him getting a grey sock on his first pick? Well, there's 5 grey socks, and there's 4 add 5 add 8, so 9 add 8, so 17 socks altogether. Okay, and then we're going to times that by the probability that his next sock is also grey, but now there's only 4 grey socks left in the drawer and 16 in there altogether. I can times the tops easy enough. 4 times 5 is 20. Now you're not going to have a calculator for this in the exam, so a bit of long multiply, and I'll do it over here. We've got to do 17 times 16, so 6 sevens are 42, 6 ones are 6, and 4 makes 10. 0 down, 1 times 7 is 7, 1 times 1 is 1. That gives me 272. So 20 over 272. The good news is that they'll all be out of 272 for this question. Okay, part B. Calculate the probability he comes to school in odd socks. So, like I said at the very beginning, let's do combinations first. So how could that happen? He could get white and grey. He could get white and black. Try and stick to a system if you can. He could get grey and white, and that's different to white and grey because it's a different way round. He could get white and black. Okay, he could get grey and black. I've lost my system. He could get black and white. Now, is that all of them? No, because I've got a double out there. Hold on a sec. Let me get rid of that one. That should have been black and grey. There we go. Okay, so I got 2 W's, 2 G's, 2 B's, and they're all different. So there's 6 combinations, 6 ways he can get a pair of odd socks, or well, not a pair, just 2 odd socks. Now then, let's have a look at the opposite. The opposite of odd socks is a matching pair. So that's grey and grey, which we've already done. Black and black, or white and white. And I guess then the decision is, do you want to do 6 combinations and add them all up, or do you want to do 3 combinations and take it away from 1? And that's definitely going to be the quickest of the options, particularly since we've already done grey and grey and got 20 out of 272 for that one. So we've partially started this method anyway. Okay, so a pair of black socks. So black on his first pick is 8 out of 17. Getting another black one, 7 out of 16. That's 56 out of 272. And a white pair, that's going to be 4 out of 17 times 3 out of 16, because when he takes a white sock there's one less. Remember, that's 12 out of 272, which means if I add all those up now to get the total probability that he's getting a pair, so the probability of getting a pair is 20 out of 272, add 56 out of 72, add 12 out of 272, that is 88 out of 272. Okay, so that's the probability that Mr. Mackenzie manages to fluke his way to a matching pair of socks. So how does that help? So the probability of coming to school in odd socks is the missing probability. So from 1, take away 88 out of 272, or 272 out of 272, take away 88 out of 272. And that is, so let's do a bit of taking away over here. 272, take away 88, we have to borrow, aren't we? So 12 take away 8 is 4, we have to borrow again from there. 16 take away 8 is 8. That leaves us with 184 over 272. That's the probability that he comes to school in odd socks. Because if he's not in a pair of socks, he must be in odd socks. They are complete opposites to each other, and that's when you can use the take it away from 1 rule. Okay. Now you do have to be careful, okay? If you had stopped here, okay, in an exam and forgotten to take away from 1, you don't get any marks, okay? Because at this point, we had worked out the complete opposite question, and the examiner will say, I'm not giving you marks for answering your own question, okay? So if you are going to do the work out the opposite and take it away from one method, you've got to remember to take it away from one, otherwise you're not going to get any marks for it, okay? So you don't have to draw a tree. You can draw a tree if you think it'll help. It can be time consuming to draw a tree, especially if there's 3 options and 3 branches everywhere. But if it helps, draw a tree. The biggest thing to remember though is that your fractions will change depending on what's already happened. So keep an eye on your fractions. Remember, and is multiplying or is adding up. And if you want to go through this without doing something silly, write down all your combinations like I did over here before you start, because it might help you to spot a quicker method anyway, but it'll definitely mean you don't miss any out. I made a mistake here and had to change one of my combinations. It does happen, okay? And hopefully then this will help you out with some questions I'll set you separately.